Greetings, Earthlings. Today we're going to return to tricky algebra and talk about conceptual maximization and minimization. I'm titling this conceptual because oftentimes when you need to maximize or minimize something, you have to do a lot of work. And here it's the case that if you can just see the concept, you can do this very quickly with almost no work, although some of the later examples will have some work. All right, so in these problems, your goal is to maximize y. In other words, what should you plug in for x to get the highest y value? So you could try poking around, and these may look kind of scary, but if conceptually, let's see what's going on. So we have this absolute value, which always returns a number that's either 0 or higher, right? It's non-negative. So it doesn't matter what we plug in for x. This will never be good for us because that's a negative. Negative 2 is always negative 2. So the more the inside is, let's say the inside turns out to be 100, then this will be negative 200. So that's going to hurt us. In other words, the best we can do is to set this inside to 0. So x would have to be 5, but that doesn't even matter. So by having the absolute value part be 0, negative 2 times 0 is just 0, so this part is gone. So conceptually, when you look at this, you know that, hey, this is going to do nothing but hurt us, so let's just get rid of this part. And the best we can do is to get 7 for y. So the maximum value of this expression would be 7. We're going to do the same thing here. We notice, hey, we're going to try to maximize this, and we see, hey, there's a square. When you square a number, a real number, it's always going to be non-negative. So this can be either 0 or higher. If x is 3, this happens to be 0, but let's say x is 7, that would be negative 4 squared. Now it's positive, but that's a negative. So this is only going to hurt us. So we want this to hurt us as little as possible, which we can do by zeroing this out. So set x to 3. So conceptually, when you look at this, you say, hey, this is negative garbage, so we just want this not to hurt us, so let's just get rid of this. And that'll be a plus 12. So the maximum here is just 12. That's why I say it's conceptual. It's fairly easy. Now, we've actually seen these problems in previous videos where we talked about applying quadratic equations to find the vertex and axis of symmetry. So this may be sort of familiar, but I thought I'd do this as well here. So here we're trying to, again, maximize, but unfortunately we're not given this nice shape where we have a perfect square. So our job here will to create these squares. So this is, if you guys remember, this is called completing the square. That's the technique. So we're going to rewrite this as y equals x plus 5 squared. Where did I get the 5? All I did is I have the 10. That's how you get that number. Whatever this is, you just have it. Now, when you do this, however, and you square it, expand it back out, you'll get 25 from squaring it. But that's a negative 7. So in other words, we have a negative 7, but that yields an extra 25, so we don't want that extra 25, so we're going to subtract that off. So together, that gives us a negative 32. So now we have what we want. Oh, sorry, this should... okay, so I messed up in the example. What was supposed to happen was this supposed to be a negative. So since this is a perfect square, in this case, it doesn't make sense to ask what's the maximum value because the larger you make this, the larger it gets. So for this one, it makes sense to ask to minimize this value. So now what's the best we can do? Well, the more we have this inside, the larger it gets, right? So we can get infinitely large. But how small can this get? This can be no smaller than 0. By making x negative 5 and zeroing this out. So when you zero this out, you're still left with the negative 32, which is our minimum. So for these, you're maximizing, and for this one, you're minimizing. And if you take a quick look, because this is a positive coefficient, again, we're going to want to minimizing over here as well. We're going to want to minimize. So this one's a little trickier because now we can't do the same trick right away because it's not a 1x, there's a 3 going on here. So all we're going to do is just divide this, factor out the 3. So we're going to have, typically you'd put double arrows, so that's why I'm making these double arrows. Okay, so factor the 3 out. So we have x squared minus 4/3 x plus 3. So I just took a 3 out of each term. If you multiply this 3 back in, you should recover that. And now once we're here, this is almost the same problem. So we're going to do completing the square. So whatever that is, you have it. So half of 4 is 2. Or you could have the 3 to make that a 6, but then the 4 and the 6 will simplify. So we're going to have 2/3. So this first parentheses is the original parentheses. The new parentheses indicates this square that we're completing. Now we have the original plus 3, but when you square this, this introduces a 4/9. So we want to subtract that off. And now by simplifying this, so that would be 2 5/9, that would be your minimum. Because like we said, oh, sorry, no, that's not the full answer, because remember, we have to multiply this 3 back in. So this part can be 0 at a minimum. So we're going to want to 0 this part out. So 3 times the 0 will be still 0, but then that 3 times that part is going to affect the answer. So the final answer is going to be 3 times 2 5/9. I won't do that out, but that's the way to do it. So number 4 is very similar to number 3, except you have to take care of this initial coefficient first. All right, so the main idea here is not to get lost in these details, but to realize we don't have to work really hard and do a lot of stuff here. We just have to see what's important, what's not important. So these squares and those absolute values tell us a lot of stuff. Those are the scary looking parts, and in fact those are the easy looking parts. So that's what after doing a little maneuvering, we can ignore them and pick off our answers. Here we couldn't, which is why I needed to do a little work first. But that's why I'm calling this conceptual maximization and minimization, and I will see you guys in the next video.